All right, so the homework starts on 322. And it looks like that. So do we got any questions on that to begin with? Okay. Let's see. All right, so this is the same sort of deal here where what you want to be looking for, two force members. Do you see any two force members in that one? Yeah, EH, okay. Now I'm also noticing that what you're doing there is you're pulling G to the right, so H, I think, to keep that thing in equilibrium, will have to pull back to the left. So that's when I look at this, that's what I notice kind of initially, okay? So what you would want to do then is realize that EH is a two-force member, okay? And then once you notice that, I wouldn't make a free body diagram of it because just turn it into forces. So if G is being pulled to the right, H will have to pull back to the left, and that'll pull E to the right. All right, so that's one thing that I notice about that. The other thing is I've got that 48-pound weight hung over B. So what that's going to do is exert forces like so on that pin. So just take those forces of the cable and put them right at the pin. It makes the dimensioning simpler. Okay, so that one is vertical at 48, the other is down and to the left at 48. So you do want to remember to include both of those, when you go through and work this out. Okay, so that's a couple of things I would notice and do off the bat there. Okay, and then I would just make free body diagrams out of the other parts, kind of turn this thing into an exploded view, and what you have then are a series of interconnected free body diagrams. Now when I look at this thing on the bottom here, which is what I want to find here, I think are the forces at D, I think, is that right? There's 4 unknowns on that. That's one too many to solve. So when I notice that, I realize I'm going to have to come in from the other direction to find one of the forces. All right, so I'm going to start with that. All right, and then probably what you'll do then is start on the right-hand side because you have a known force there and start working your way through. Remember, you don't have to completely solve these things out. You really want to look at these and develop a strategy to work your way through. Right, so that's how I would consider these as I work through them. And what I'm seeing there are all those supports down at the bottom. The likely thing to do here is going to be to take moments about those supports and just start to work your way across. So I think if you work on GHI, you can get EH, and it's 45, okay? So EH then is 45. Okay, and so that will make this one 45. And then if that's 45, you can once again, you can do a moment there, I think, about F, and then you'll get F dx. It will be 20. And once dx is 20, it's 20 there. And then from there, you should be able to solve out for dy. Okay. And it's 51.6. So the deal on this is that the first thing to do is to look at that lower piece there, the one, at least the one that got drawn on the bottom, and realize that there's one too many unknowns there to be able to solve it out independently. And once you see that, you've got to get one of those unknowns, either cx, cy, dx, or dy, from a different source other than that free body diagram. And what you can do is work your way in from the right-hand side then and get dx at 20. Once you've got that, you can find dy. And you want to remember to be turning things around as you go from one member to the next. So, do we have any questions on that? Okay. So that's the basic strategy on these frames and machines. On this one, you have that identifying the two-force member, EH, and also handling that pulley by putting the forces right on the pin. That's the way to address that, okay? Just makes the dimensioning much easier, and that's the standard way of handling that. So these two go right at the pin, okay? Okay, then we get to this one. A little bit of a pulley system going on with this thing. Actually, why don't we go ahead to the one ahead? This one. Now, when you're doing this, what you want to do is to identify how many cables you've got. It's always important to do that. So, I just start at the beginning one and just track it through. So that'll come around like this, up and over. So that looks like one cable, okay? So one key thing to do first here is to figure out, how many cables you've got. We got one right there. Now, when I see we've got one cable, I know that the force is everywhere the same in that thing, okay? So it's, whatever the force is, whatever that F is, it'll be everywhere in that cable. And then from there, what you want to do is just cut a free body diagram around something that you know, where you have a known force, so you can solve for the thing you're looking for, which in this case is the cable force. So I would just take a free body diagram about one of those weights. They're 600 each. I don't know as it would, because going around the pulley, you don't really have a known force unless you've extended all the way down to the weights. So, you need something known to work off of to find the unknowns. So even though I know the pulley's got a lot more going on, it's kind of the center of what's occurring with this thing, I think a free body diagram like that would be the way to go.
So you're doing.
Oh, okay. Yeah, right, okay. You meant the lower pulley. Okay, I get it, yeah.
Yeah, the upper pulley would be kind of crazy.
Yeah, right. That was my thinking. So, yeah, this one, when you cut through something, don't overthink it. Those cables pull up. They always pull. So you got two cables pulling up and 600 pounds going down. So pretty straight up there, okay? Everybody okay with that? Any questions? Okay. So that's how you handle the pulley problems, okay? All right, now this next one here, a little complicated there. I want to do that pulley problem first because we got pulleys going on with this one too. Now, do you see any two-force members on that one? BD. Unfortunately, yeah, BD extends onto E, so you can't just, it is BDE, so it has to be treated as that.
I'm not seeing any.
Yeah, I'm not either. So yeah, there's no 2 force on that. So don't invent them. You know, they may or may not be there. If they're there, find them by all means. But if they're not, they're not. So, and there's a pretty big tip-off. I mean, BDE is one member and has 3 pins on it. ACD is one member and has 3 pins on it. So neither of them are 2 force members. Okay. So you can't really use 2 force members on this. Now, what you're going to want to do is you're going to want to figure out the forces at D on this one. Now, the cable is something you're going to have to deal with. So what I would do, I think, first would be to figure out what the force is in the cable. All right. And that would be similar to what we just did. I mean, very, very similar. You just kind of, I would make a cut like that to find the force in the cable. All right. Now notice that is one cable. You could track it through. And, you know, if you track it through, you'll see that it is indeed just one cable. So that thing comes down, around, like that. Pulls down, okay? All right, so you find the force in the cable, and why don't we just call that T, okay? Just to give it a name. So cable force, we'll call that T. And then once you've got that, you could put the cable force at the pins. All right, now one thing on this is you can't just move one cable force to a pin. If you move them, you got to move all of them. So what I mean by that is, okay, I've got one force of T right here. That's already there attached to point E because there's a cable up there. Now I'm going to have to move both of these to the pin. So there would be a T going that way plus a T going that way. I'm going to move them both.
The way you drew it, it kind of looks like there's 2 copies going down.
There are, yeah.
Oh, right.
Yeah, okay. Yeah, so yeah, we got the 2 there. And similarly, over there at C, put both of them, move them both to the pin. So I've seen people make this error before where they'll move one to the pin but not the other. You can't do that. You got to move them. You got to either move them or don't. Okay. So if you move one, you got to move the other. All right. So after that, they just become forces. Okay, so what you're going to have then are free body diagrams, something like that.
Does that mess with your moments though?
Well, moving only one is what messes with the moments. If you move 2 of them, you mess with the moments, but in a compensating way. You know, you're moving them both the same amount, so the moment effect is canceled, which is what you want. Yeah, okay. All right, so then you get free body diagrams that look like that. And you've got that same sort of problem there on the top one. You got bx, by, dx, and dy, 4 unknowns. And on the diagonal one, you got ax, ay, and dx. And I already put the answer on here, but it's dy. So you have 4 unknowns on that also. So, you know, you got a little bit of a problem there because you can't completely solve a member with statics if it's got 4 unknowns in 2D. It's just 1 unknown too many. But if you've got a vertical or a horizontal, what you're going to have is you can find a point where 3 unknowns intersect quite often, and that would be the point there. So I think what I would start with would be sum of MB equals 0, okay? Because that's going to eliminate bx and by, of course, but also it'll eliminate dx. So given that, you can solve for dy. So dy, as is shown below, comes out to be 2133. And then you come on over here and get dx. So that's a common strategy on these. And dx will be 3009 or thereabouts, okay? Or you kind of work one off against the other. If you got one horizontal or vertical, things quite often line up very well. But you do have to do the stuff, figuring out the cable and moving the forces over to the pins before you start in on this one, okay? We got any questions on that? All right. All right. All right, then we got these centroid problems. So what you want to do with these is break them up into pieces. Okay, this is 361. 341, okay, 341, thanks. Okay, so this one, pretty obviously, you're going to cut it up into a rectangle and two triangles. Find the areas, okay? So the rectangles, so what, 12 by 6? So that's 72. And the triangle is 3 by 6, so that's 9. Okay, just remember the 1/2 when you do the triangular areas. So I start with that. And then want to find centroids, okay? So the x centroidal distance is measured over from the y-axis, and the y centroidal distance is measured from the x-axis. And so you just measure over and get those centroidal distances there. Okay, now remember, you've got to hold whatever axis system you start with, and so I give you the axes on these. So you got to use this x and y axis throughout the entire problem. And you'll notice that that I've got those distances marked on the page. That keeps me from making any sort of foolish errors there. Okay, so we've got 6 over and 3 up for the rectangle. I'm just taking half of 12 and half of 6. All right, and then I've got one more I show you there, which is the distance up from the x-axis to the centroid of that triangle. You're going from the vertex up, so it's 2/3 of the height, so 2/3 of 6, which is 4, up from the x-axis to the centroid. So what you're going to want to do then is find these other centroidal distances. Now when you do this one, remember to include that 12. You know, it's like you got to go 12 over before you even get to the triangle, so remember to include that. And then you've got these other two. Okay. So you'll see something like this on the final. So just be sure that don't take this stuff for granted. Just be sure you're doing these and you can knock them out, There's a very systematic process to get these figured out and just get that worked out in your mind so you can do it when you're taking the final, okay?
See that same kind of table?
You don't need to do a table, but you don't have to, but it's how I present it, I guess. So all right, so those are the distances you need, and then the rest of it is just kind of a mechanical process. You take the area times the centroidal distance for x and y, and you come up then with an x bar A and a y bar A for each independent part, 1, 2, and 3. So 72 times 6 is 4320, 72 times 3 is 216, etc., etc. And then what you do is you add up and get the total area, and add up and get the total x bar A and the total y bar A. You sum those up and then just divide x bar A over to the total area and y bar A over the total area. All right, so you get the areas, get the offsets from the two axes, then multiply the area times the offset and get x bar A, and do the same thing for y bar. And you've got those formulas on your formula sheet. And then you just add up the three columns, get the total area, get the total x bar A and the total y bar A. And when you've got them, just divide them out. You'll get the centroidal distance. After I've got it, I plot it up as I've done there on that bottom sketch, just to make sure it makes sense, you know, that I'm not doing anything kind of that looks crazy or, you know, odd. Okay. Everybody okay with that? We got any questions on that one? Now be a little careful, you know, nothing too big, but that one triangle is below the x-axis, so it has a negative y-bar, okay? So that triangle number 3 has a negative y-bar because it's below the x-axis. Okay. All right. All right, now this one has a cutout out of it. So on this, I would set up to do a cutout. It's got a semicircle, a rectangle, a triangular cutout, and then another triangle on the end. So it's the same sort of drill here. You just want to find the areas. Now the first one is that triangular cutout. So remember, if you do it this way, to include a negative on that, because that's negative 144 for the areas. Okay. So we're doing all right with that, those areas there? You got a rectangle and that's a semicircle there, so that's 226.2 pi r squared over 2, I think, for a half of a circle. All right, and then what you want to do next is you want to find the centroidal distances. Now that's a semicircle, so what you're doing with a semicircle is you're using that formula. Now the formula is actually for a quarter circle. And what that'll tell you is that these distances here, this one and this one, they're the same. They're 4r over 3 pi, right? I think. Always get this thing mixed up. All right. Now, what that means, if you have a semicircle and you're given that formula for a quarter circle, is you can figure out the centroid of that semicircle pretty easily. See, it's going to be right on that midpoint line, and it's going to be right on that middle line that extends vertically down through, because that's a symmetrical figure. Those centroids are equal distances away from that midpoint line. So that's where the centroid will be in the x direction. In the y direction, it'll be the same thing, 4r over 3 pi. Okay? So that's how you can find the centroid of a semicircle. Just use the quarter circle formula. Yeah, 4r over 3 pi, like so, okay? Now, I have had people try and, when they have these, in this particular case, they try and use that 4r over 3 pi in the x direction, but you don't use it. It's just in the middle is where it is, okay? It's just the radius distance over from one side. There's nothing trickier about it than that. It's in the middle, okay? Just think about a balanced line. That's where it would run, okay? All right, and then once you got that, You got x bar, which is in the x direction, y bar is in the y direction. So x bar is measured from the y-axis over in the x direction, and y bar is measured from the x-axis up and down in the y direction, okay? And then you just figure out where those centroids are at. Okay. So, you know, I've got some of those filled in there. 14 up, the y bar for the cutout rectangle is 18 up. And what's going on here is we're going 18 from that dimension over on the right. But then we got to come back a third of that base, which is 12. So a third of 12 is 4. So we're going 18 up and we're coming back 4 to get to this centroid right here. So, and this is going to be kind of messy in here, but you're going 18 up, but then you got to come back 4. That's the idea. Okay? And that's how you get from the x-axis up to that centroid. 18 minus 4. Okay? We're good with that? Okay. If you want to get to that centroid of the cutout triangle in the x direction, you got to start at the y-axis. What you've got there is you got 12 over, so you're going to go 12 to the right, but then you got to come back a little bit again. You got to come back a third of that total base there. 12 and 12 makes 24. So you go 12 to the right and then a third of 24 back. So 12 minus 8 is 4. Okay. And, you know, you just figure out these different centroids here. Going down to the semicircle, you're going down 18 to get to the base of the rectangle, and you go minus 4r over 3 pi more. So you're at negative 23.1. All right, so you want to get those distances figured out in the areas, and then once again, just put it in a table, okay? So 4 parts to that, get the areas of each part, and then get the x bar and y bar distances, and then multiply and add up the 3 columns, okay? The area, x bar, y bar, x bar A, and y bar A, okay? And then you take x bar A over the total area and y bar A over the total area, and get the centroids there. Okay. And I got a little typo there. That's centimeters cubed is what that ought to be on that column, I think. Yeah. Okay. Any questions on that? Okay. All right, so that's how you go through those. Okay. All right, why don't we go through some more of this moment of inertia stuff. So let's have a look a little bit more at this. So this is, as I was saying, it's another shape property that we're working through. And this is something we're going to look at called the transfer axis theorem. So this is on 680 and 682. So the deal with this is you don't, a lot of times we're working with composite shapes, okay? And what you have commonly available to you are tables that show the moment of inertia of a shape about its own centroid. That's the common way that this is done. I think I've locked this thing up again. Turn this thing. So when you look at tables, they're generally going to be about the centroidal axis. Let's see. I don't even have it. There we go. But if you take composite shapes like this T-beam, you might be finding moments of inertia about an axis other than the centroidal axis of the parts. Okay. So if I've got that T-beam and that neutral axis running as shown, I'm offset from the centroids of each of the rectangles that make up the T-beam. So to find this moment of inertia, I'd find the moment of inertia of each shape about the neutral axis and then add them together. That's all I got to do. But I have to account for the fact that the axis I'm using, i.e. that neutral axis, doesn't run through this centroid of either figure, okay? So there's something called the transfer axis theorem, also called the parallel axis theorem, that I about an axis other than the centroidal axis is the centroidal moment of inertia, I bar, plus the area plus the offset distance squared. It's called the transfer axis theorem. So this is a way of finding moments of inertia about an axis other than the centroidal axis. Okay. And I've got a little bit of a derivation there for you. I think it's on 382. So let's say we've got this shape, and we're going to find I bar sub x for this thing. And there's our axis. What you would do is you would find the integral of the offset distance y, and I've drawn a couple of those offset distances in there, squared, times the areas. So integral of y squared dA. Well, if I take that axis and I offset it a distance of d, so if I put that axis down here, and that distance is d, what's going to happen if I want to find I sub x now, not I sub bar x, but I sub x, is I would take the integral of y plus that offset distance d quantity squared dA. So every one of these dA or y distances, I'm going to have to add the offset into when I recalculate for that lower x-axis. So that distance will no longer be y, it'll be y plus that offset distance d, okay? So what I'm going to have there is I'm going to have this thing y plus d squared, and I'll just FOIL that thing out. So y plus d times y plus d I'm not sure what FOIL even means anymore, but multiply the first term.
Outside, inside, last.
Is that what it is? First, outside, inside, last. That's FOIL. Okay, so it does make FOIL. Very good. Okay, so I'll get y squared plus d times y. Now that's not a calculus dy. That's a d plus times y. And there'll be two of them, right? Because I'll have the one on the inside, another one on the outside. So I'm going to have y squared plus d times y. And then I'll have the last term squared, d squared, okay?
Wouldn't that be 2dy?
Probably, thank you. There we go, thanks, 2dy. Okay, so that's what I'd integrate with respect to a, and that's what I've got right here. Well, what happens here is the d is a constant, so I could make this into three different integrals: the integral of y squared dA, integral of d squared dA, and the integral of 2dy dA. I could pull the 2d out because it's a constant. D is just a constant distance, and of course the number 2 is. That leaves me with y dA. Okay, now if I'm referring this to the centroidal axis, because it's a centroidal axis, half the y dAs are above the axis and half below. So half of those y's are positive and half are negative, and that'll all multiply out and become 0, okay? If you're at the centroidal axis, the integral of y dA is 0, okay? Because that's part of finding the centroid is what that is, that little integral. So that middle term zeroes out, okay? So I'm left with the integral of y squared dA, and that's just I bar x. Okay, right here, I mean, that's I bar x. Then I'm left with the integral of d squared on the outside of the integral. That's a constant, times the integral of dA. Well, the integral of dA is just a, the area. So that gets me the ad squared term. Okay. So those three terms, the first one's I bar x, the second one zeroes out, the third one becomes ad squared. So that's where this transfer axis theorem comes from. Okay. Y'all okay with that? Good. All right, why don't we use this thing one more time? Let's go back to where we were finding the moments of inertia of a rectangle there. Page 660. All right, we could use this to find the moment of inertia of a rectangle about its own base down at the very bottom, because you know the centroidal moment of inertia of a rectangle, right? So I bar sub x, which would be an x-axis through the centroid, for a rectangle ought to be bh cubed over 12, right? We derived that a couple of days ago. A day ago. Okay. And then what we're going to do, we're going to add in a. Well, the area of a rectangle ought to just be base times height. And then the offset distance ought to be what? Yeah, half the base. There we go. So we just plug that stuff into the formula. We can work it back. We might have to do a little bit with fractional type stuff, but we could work that out. So we're going to get bh cubed over 12 plus ad squared. A is bh and d is h over 2. So bh cubed over 12 plus bh, h over 2 quantity squared. Bh cubed over 12 plus bh cubed over 4. You'll remember your basic fractional stuff. Find the common denominator. Remember all that? Okay, so bh cubed over 4 is 3 bh cubed over 12. They're equivalent fractions. Add them up, you get 4 bh cubed over 12, which is bh cubed over 3, which is the same thing we got from doing the calculus right above that, okay? So that's a little bit of an application there of the transfer axis theorem. So that's the moment of inertia of a rectangle about the x-axis shown right there. Okay. And one thing to keep in mind here is there's a different nomenclature that's used. For a moment of inertia, you name the moment of inertia after the axis you calculated about. So that's I sub x. Our distances are measured in the y direction, aren't they? Okay, off of that x-axis. Whereas with a centroid, centroids are named about the direction they're measured in. So there's a different kind of nomenclature there. Yeah.
So I sub x indicates how hard it would be to bend the beam if you push in the x direction,
Actually, if you push normal to the x-axis. So if this thing were a beam, well, why don't we go to the next one here? Let's find the moment of inertia of this thing. I don't think I've got a picture of this, so you can just draw it up. So what this thing is, and I'll sketch it maybe while you're working on it here. If you have a T-beam, like so, I'm going to get away with this. I don't know. So if you push down on that beam, what we're doing here is we're seeing how it would bend about its own neutral axis, which runs here and also runs the length of the beam. So this number will help us determine how much flex you're going to get in the beam like that. And I'll just draw that much of it, because if I try and do more, it'll turn into a mess, okay? So the force is pushing normal to the x-axis along the length of the beam. What we're looking at there is a cross-section of the beam. Okay.
And
So
that particular bend right there is the compression, and below the neutral axis would be tension, correct?
yeah, right, yeah. This side's, no, this side is compressing, yeah. Below is in tension, yeah.
Yeah.
Yeah, okay. All right. So if you're going to find this moment of inertia, you could, if you're going to use the transfer axis theorem, you'd find the moment of inertia of each piece about its own centroid. And then use these distances here. Call it D1 and D2. Okay. That's how you'd find the moment of inertia of that.
And once you found the moment of inertia for each piece using the transfer axis theorem,
It's additive. Yeah, it's an additive property. Yeah. Just add them up. So you're going to go BH cubed over 12 plus AD squared. And actually, if you wanted to shortcut a little bit, they're both about the base there, so you could just go BH cubed over 3 for both pieces and add them up. You'd get the same answer. So what I'm doing there, I'm taking the base of the top one, which is 12. Its height is 4 cubed over 12 plus its area, which is 48, times that offset distance from the neutral axis to the centroid, which is 2, and I square the 2. Add that all up, and I'll get 64 inches. And I've got a little bit of a typo there. That should be to the 4 right there, to the 4, and then 94 inches to, or 192 inches to the 4. 256. That's for the top piece. For the bottom piece, 3 for the base, 8 high. Cube that, divide it by 12, plus 24, which is the area, times 4 squared. and that's 128 plus 348, that's 512. Add everything up, you get 768 inches to the 4. Now, one thing to notice here is because you're squaring the distance, the sign is somewhat irrelevant. This is actually -4, but when you square it, it comes out to be a positive number. So even though that's below the neutral axis, it is not a negative. The only reason you'd have a negative is if you had a cutout. That's the only reason. Any solid material will have a positive moment of inertia. Okay.
You always use the neutral axis.
You don't have to.
But that's what the opposite.
In the practical world, you do, yeah, because that's what a beam bends about. But in a textbook, you can put the axis anywhere really. Okay. Now let's see. I like to use tables for these, but I guess we'll get to those tomorrow. So we'll cover the rest of this tomorrow. And I'll just I don't know if this will be the last assignment or not, but anyway, we'll figure that out. What I'm going to give you are 361 and 362. I use tables at least for that second one. So 361 and 362. I don't know, that's a good question, isn't it? Probably just make them due next week. We'll go over them thoroughly. They'll be due at the final. Which is, the final's actually Tuesday. We'll talk about that. I'll get you a review tomorrow, I guess, and we'll talk about that. We'll talk about when the final is tomorrow, too. I think we're going to have it Tuesday, but we might, I don't know. We'll think about that. For sure it'll be Tuesday at 2:30. Some of you got physics right after that, though. Is that a lot of you, or what's up with that? There's like a Tuesday physics now. Okay, so we'll talk about it tomorrow a little bit.